Good morning. My name is Scott Tenaglia, and today I'm going to talk to you about a tool my colleagues and I wrote called ACSploit. And this tool is designed to exploit algorithmic complexity vulnerabilities. So the way this talk is going to shape up, first we're going to introduce algorithmic complexity vulnerabilities to those of you who don't know what they are. We're going to talk about why we developed this tool to exploit them, and then we're going to do some demos. But first, I'd like to acknowledge all the folks that helped design and build this tool. You see their names and faces here. And I'd also like to thank the Defense Advanced Research Projects Agency and the Air Force Research Laboratory for sponsoring this work. All right, now let's get into some details. So, algorithmic complexity vulnerabilities are a type of resource usage attack. And the idea behind them is that you want to trigger a program to use as many resources as possible using as few input bytes as possible. So in a very sort of dry academic sense, we have this graph down here on the right. On the y-axis is resource usage measured in either time or space, and on the x-axis are the input bytes that you supply to the program. So we'd like to identify this shaded area and say that a program is vulnerable to an algorithmic complexity attack if you feed it less than b bytes of data and it uses at least a amount of resources. So in this example, there are two programs whose asymptotic runtime complexity are both linear. One's labeled C, one is labeled D. For C, there is some collection of bytes less than B in size where it will get into this shaded area, and for D, there isn't. So C is vulnerable, D is not. Now, in the real world, we don't have these hard and fast limits, right? What we say is, in terms of time, that the CPU will be spun to 100% utilization for, let's say, 3 minutes, and we'll call that a successful attack. Alternatively, in the space types of vulnerabilities are either in RAM, so we chew up large amounts of RAM, or large amounts of disk space. And you've seen these types of things before, you just might not have known what they were called. So for example, decompression bombs are a real classic example. Probably one of the best known examples is 42.zip. This is a 42 kilobyte zip file that expands to 4.5 petabytes on disk. I don't know about you, but I don't have 4.5 petabytes on disk, so this is probably going to cause some issues to my system. Another classic example are hash table collisions. We're going to go through a specific example of CVE 2011-4858 a little later on. And then if you go to these kind of security conferences a lot, you'll see them crop up from time to time. In 2016 at Black Hat USA, there was a Came to Drop Bombs that talked all about decompression bombs and how to use them for pen testing. That resulted in the bomb.codes website, which has pre-canned compression bombs you can just download and use. And then DEF CON 23, there was a regular expression denial of service talk. This is actually, OWASP even identifies this as a type of vulnerability that you should be looking for. Basically, you can create regular expressions that when you attempt to match certain strings to them, it takes the regular expression engine a very, very long time to try and match those strings. So these are the kinds of things you might have seen and just not known they were algorithmic complexity vulnerabilities. So where do they come from? Well, go back to your undergraduate algorithms course. Every algorithm has a best and average and a worst case. It may be vulnerable to an algorithmic complexity vulnerability if we can reliably send input to that algorithm that will trigger its worst case, provided we have enough input bytes we can send to that algorithm. As a canonical example, take bubble sort, right? It can be written in less than 10 lines of code, which is there on the bottom left of the screen, and it simply sorts items in a list. And it does so very naively. All it does is it looks at two adjacent pairs of items, and if they're not in order, it puts them in order and then moves to the next adjacent pair of items. In the best possible case, all the items are already sorted, so all bubble sort has to do is just check that list. It goes through that list one time. In the worst possible case, when you have things in reverse sorted order, it has to swap pairs, every single pair, and then it comes back through the list again and swaps slightly less than every pair, and then slightly less than that. And so you get this n-squared complexity in the worst case. So that's kind of where they come from, but why do we care about them, right? What are the properties that make them interesting? Well, they're really only good for denial of service effects. And you might think to yourself, who cares, big deal, doesn't really matter. Except for the fact that you're used to thinking of denial of service conditions as distributed denial of service attacks, right? Something where we commandeer a lot of hosts, maybe in a botnet, and we send lots and lots of traffic to a network service to take it down. What we're talking about here is the ability to send a single packet to that same network service, but cause the same effect. Spin the CPU up to 100% utilization for some period of time. Other types of effects in the space area, we can consume lots of RAM, which should do one of two things. It might crash the program because it can't allocate more RAM, or it might cause massive swapping to disk, which has consequential effects on other programs. Similarly, if we fill up the disk space, what might happen is your program might crash because it's trying to write to disk, and it can't, but really it wasn't your program that caused the problem. Another program in the system might have actually filled up the disk space via one of these attacks, so you again get those second and third order effects with these kinds of vulnerabilities. Another interesting property besides denial of service effects is that they're difficult to fix. These aren't bugs. Bubble sort, for example, is supposed to be able to sort any list of items, right? It doesn't matter if they're in reverse sorted order. It just happens to be the case that will do much more work when they're in reverse sorted order. So there's not an actual bug to be fixed here. What you'd have to actually do to fix it is to swap out the algorithm. And here's why that might never occur. A commercial vendor who is in a very difficult market might depend on performance of their product to beat their competitors. And if you said to them, hey, you have a really bad worst case in your product, they say, well, my average case is really good, and I'm unwilling to swap out another algorithm that has a better worst case for a worse average case, because then they're going to lose market share. And thirdly, they're very difficult to defend against, right? There is nothing wrong. There's no signature you're going to write in an IDS for numbers that are put in a particular order, right? All of these are expected inputs to the algorithm. It is supposed to be able to handle them. So how do you write something to defend against them? Why my company cares about this is because in 2015, we started working on this program for DARPA called Spacetime Analysis for Cybersecurity. This whole program was designed to be able to detect algorithmic complexity and side channel vulnerabilities in Java programs. It was structured as a capture the flag competition. So there are research and development teams coming up with automated program analysis tools to look at Java code and find these. And then there was us. I ran the control team. The control team was just a group of folks who are good at VR who were sitting down with readily available tools, manually going through code trying to find these. If the R&D tools did better than we did on a particular competition, then the research was winning. If not, we were winning. So we ran into some really big problems with this. First of all, every competition had tens of binaries, so between 20 and 30 binaries. Each of those could have had tens of thousands of lines of code in them. Each of those could also have had multiple potential vulnerabilities. So there's lots of algorithms implemented in each of these. How do we know which ones are vulnerable? And by the way, the competitions are time boxed, right? They're constrained by time. And all we had to use were existing tools like debuggers, decompilers, and profilers. So triage for us became very important. We need to be able to find an algorithm and immediately determine whether or not that was vulnerable. We need to fire some input at it that says you are vulnerable or you are not. Of course, if it was a known algorithm. And that's where ACSploit comes in. So what we did here is we figured out a way to generate the worst case inputs to a bunch of known algorithms. And the tool itself presents as an interactive command line utility styled like Metasploit. We wanted something that was both familiar to us and familiar to other folks, the pen testing community, essentially. It is implemented in Python 3, fully open sourced at GitHub. You can go there now, download and play with it, and we encourage you to do so. And it's released under the BSD 3 license. So there's four main components to ACSploits. One are input generators. What kind of input do you want me to provide to that sorting algorithm? Do you want it to be integers? Do you want it to be strings? Do you want it to be floating point values? Then output generators. How do you want me to give you that output? Print it to the screen, put it in a file, send it over a network connection? Third, constraints. Maybe you're trying to get past a web application firewall and you can do all alphanumeric characters except for the letter K for some odd reason. So we have the ability for you to generate those strings just without the letter K in them. And then exploits. Exploits are the individual modules that will generate those worst case inputs. Currently, we have over 30 of those modules in the program. You can see we have everything from decompression algorithms to non-cryptographic hash collisions, sorting, searching, and a bunch of other data structures that you might not even have realized you could potentially exploit. So now what we're going to do is I'm going to switch to a few demos to show you how we use the tool. Okay, so in each of these demos, we have three windows. The top is going to be some sort of resource measure. Here we're looking at CPU utilization and RAM. And the bottom left is going to be the ACSploit tool itself, and then the right is going to be the target. So if we hit the login button for this target, this comes from the Stack program. The idea behind this web application is it's going to plan routes for airplanes to fly. And what we were asked to do is see if we can find an algorithmic complexity in space vulnerability. So could we take up 1.1 gigabytes of RAM with this by finding a vulnerability in this program? So one of the things we noted is that a route map, you have to be able to upload a route map in order to determine routes. You could upload this route map in multiple formats, JSON, XML, etc. And so we know that XML bombs are a thing that exists. So what we can do here is we can type show in ACSploit, and it'll give you the list of available exploits, and we start off with bombs, and we look under compression, and then we look under bombs XML billion laughs. Now, you might not know what the billion laughs attack is, but you don't have to. You could just say use, type info, and it will show you what the billion laughs attack is. It gives you a short little description. And in this particular description, we find that we can go to Wikipedia and find a much more in-depth discussion of this type of attack. So what we're gonna do now is we're gonna type options. And we see that the output generator for this is going to send it to a file. Sounds like a good thing because we have to upload it as a file. The file name, the options for this output module, the file name is going to be ACSploit output. We don't really like that. That's kind of long. So what we can do is we can set file name, and we use tab completion here a lot, to bomb.xml. And if we keep going down, there's not a lot of other things we want to change in the output, but for the exploit options themselves, the memory impact we do want to change. Remember I said that we were challenged to take up 1.1 gigabytes of space? This number's in megabytes, so right now we're just talking about 1 gigabyte. So what we'll do is we'll set the memory impact to be type options again. Everything looks good, so we'll hit run. Okay. Now if we go over here and we do an ls-l, we see that bomb.xml was in fact created. It's only 779 bytes. And if we cat it, we'll see that it is in fact a version of an XML entity reference, a recursive entity reference attack, okay? And the size of this file is based on that memory limit that I put in. So now we go back over here, hit browse, click on bomb.xml, upload it, give it a name. You have to give everything a name. Now, focus on this 103 megabytes up at the top here for memory usage. When I hit submit, you'll notice two things happen. One is the CPU utilization goes up to 100%, and the other is that the memory usage starts to climb really high, right, very quickly. It started off at 100, it's almost at 300 now. With this particular example, the way it processes this XML file, it'll peak at about 600 megabytes for a couple of minutes, and then it'll go up and it'll go well past the 2 gigabyte limit for this container. And in fact, it'll crash this container. We're not going to wait for it to do that because this is only a 25-minute talk. Instead, we're going to kill it so that it doesn't actually take up all the memory and move on. The next example we have is also from the Stack program, and this is, again, something you might find in the real world when you're pen testing web apps. This is a message board style application. You can look at threads, you can click on a different thread, and you can add a new message. Now, one thing that this program has, it has a line breaking algorithm in it. So line breaking algorithms, if you're not familiar, takes a single line of text and tries to figure out the most optimal place to insert a new line such that it's formatted well for your screen. Now, it turns out that the most naive way to implement this algorithm, kind of like bubble sort, right? The most naive way to implement this algorithm takes exponential time. So we'd like to test, without even looking at the code, whether this exists. So again, we type show, and we go down to our set of string algorithms down here, and we see this first one says strings line breaking. So again, we select it, say use, type options. And we see that in this case, the input it's going to generate for me are sets of characters, and the output is going to come right to the screen. This also shows where you can do some of the restrictions. So the minimum and max value here for strings it's going to generate are clearly alphabetic lowercase character set. We could add restrictions like saying don't include K, but for right now we're just going to keep it as it is. And for the exploit options, the basic string we're going to generate is going to be 120 characters in length. So if we run it, we see what it gives us is just a set of A's separated by a space. That's not terribly interesting. Technically, those are words, and that's how line breaking algorithms work. They try to find the spaces and then figure out where to insert a new line. So let's do something different. Let's set that string length, right, something bigger. Let's set it to, let's say, 1,000, right, and see what happens. So what we can do is just copy and paste it right from the screen into this message, hit post, wait. Okay, well that came back pretty quickly. So I guess 1,000 words isn't going to do it. So let's just add a 0. See what happens here. Run it again. Copy, paste. Taking a few more seconds, comes back fairly quickly, but then we see this spike up here of the CPU. So it looks like we're getting closer. So why not just add another 0? 100,000. Again, we copy, paste. And now if we watch the CPU utilization up here, we'll see it spikes to about 100%. If the website itself is not returning, right, it's kind of showing this not returning, and it will actually sit here for several minutes, continuing to spin. So we've successfully determined that this is using a naive string breaking algorithm. Now, this could have been a different string algorithm. There are several others in here. This was the first one on the list, so it's the first one we tried, and it happened to work. but it also shows the ability to kind of iteratively go through and test different test cases for these programs. Again, we're going to kill it because we only got 25 minutes here, and we don't want to waste it looking at that CPU spin to 100%. All right, so those are things that came from the STACK program. Those are examples that we were working with. But let's talk about some real-world test cases. In 2011, there was a CVE release for Apache Tomcat, and there was an issue with form parameters that were submitted to a Tomcat JSP application. Essentially, what would happen is the variable names would be put into a hash table. So there's a potential that if those variable names collided, the actual names of them had a hash collision, they would be stored in the same bucket, right? So a typical standard hash collision attack. But you had to send them as post values as well. So what we were trying to do with ACSploit is determine, could we create these hash collisions of HTTP post form variable names and then submit them as a post request. And so we're going to show how we can do that with ACSploit. So the first thing we're going to do is we're going to show the number of algorithms again. Since this is all implemented in Java, we were talking about Java hash collisions. So we'll pick the Java fast hash collision algorithm. And we'll look at the options. So first thing we note is that we're going to output it to the screen, and we're going to use a set of characters to create these strings. Originally, we're going to do 10 collisions, so why don't we just run this and see what it comes up with. And we see here that we get 10 strings, 8 characters in length each, and those are all going to collide to the same hash value. So that's pretty good. But we said we need these to be form parameters, right? So it needs to look like URL encoded parameters. So we can do that very simply with ACSploit. If you see here, there's a separator option on the output, and right now it's set to new line. So that's why there's a new line, that's why each of these values is on a new line. But what we can do is we can set the separator value. Tab complete, it actually shows us what we can set it to. So we can set it to a comma or a new line. But what we're interested in is custom. And we're going to set equals and ampersand to these values. Now if you look at the output, what does it look like? It looks like a form variable name, equals, it has no value to it, ampersand, connecting the variable to the previous variables all the way down the line. So that looks pretty good. That's like something we need to submit to the web server. Now we could do this. We could generate a lot of these, somehow figure out how to send these maybe with Netcat or something, but there's an easier way to do this in ACSploit. What we can do is we could set the output generator. We set the output generator to be HTTP. We type options. Now, the input generator is the same, the output generator is HTTP, and we have this new set of options to play with here. Okay, so the first option we want to set is we want to set the URL. We look in here, we just grab the URL of any JSP page, because any JSP page will do. And then we look down, we say, okay, the separator value, right, we need to set that separator value like we did for the other output. So we say set separator custom equals ampersand. As we keep looking down at these different parameters, well, we know the method has to be different. So if we say set HTTP method, and we can tab this as well and say, yep, post is supported. Content type, remember we said these are URL encoded form parameters, so we need to say content type equals application x www form URL encoded. All right. And then there's one other parameter we need to set, which is use body. We need to say, yes, please send these parameters in the body of the HTTP request. Okay. This all looks good. Now, something else we're going to do is we're going to set the number of collisions to be really high. We don't want to just create 10 variables here. What we want to do is we want to say, let's say something really big, like 50,000. This other value down here, we're also going to set. This value determines how big the output is going to be, how big those strings are going to be. So there's this trade-off between time and space. If I set that value to something like 100, it's going to take longer to generate those strings, but the strings will be smaller. Because this is a live demo, we're going to set it to a smaller value so it runs quicker. So one last check of all the options, 50,000 collisions, sent to that address. Let's run this. Generating the collisions now, and it tells you that it's now sending a slightly less than 2 megabyte HTTP request to the server. Now this is important because Tomcat will not process requests that are over 2 megabytes, so we're below that limit, which is good. And then we see up here that the CPU is spun up to 100% utilization, which means we successfully triggered the worst case complexity of this algorithm. So this is important because if you're doing a lot of this kind of web app pen testing, you can do a lot of what you want to do for checking for algorithmic complexity vulnerabilities right within this tool. And like the other demos, we're going to kill this. All right. So there's one other example I want to show you. Here, the resource monitor is size on disk. So there's a 58 gigabyte disk in this container, and currently there's 4 gigabytes being used. And over here we have the standard CPU measure. What we're talking about here is the Caracol file server. This is an open source file server. It's actually a multimedia file server. And the idea is you can upload different kinds of multimedia files, do a few things like resize, generate thumbnails and whatnot, and then effectively just share them, right? On the back end of this program, it's using a package called Graphics Magic. Graphics Magic does all the actual processing of the image files. So we want to see if it's potentially vulnerable to some sort of image compression bomb. So again, we're going to type show, go up here to the bombs, and see there's a whole category for image bombs. I like PNG images, so why don't we start with that. And we look at the options here. And again, we notice it's going to output to a file. Let's change that file name again to something else, like bad.png. None of these other options seem totally relevant. And this seems like a good size. So if you look at the exploit options here, 225,000 pixels by 225,000 seems to be a pretty big image. So we'll actually leave it at that. We'll leave it at the default. And then we'll just type run. This will take a good 4 or 5 seconds to generate this file. And again, it tells you how long it took to generate it, 7 seconds in this case. And we do an ls, and we find that we get a 6 megabyte file, which is not a super small PNG, but it's not too big either. We'll just go over here then, hit the upload button, click on bad PNG, and upload it. And note that we were at 4 gigabytes, and now we're slowly climbing up, right? Now we're at 7, we're at 8, and CPU is spun at almost 100% utilization. And then the size, the amount of data taken up on disk will continue to increase. In fact, if we let this go, it will take up all 58 gigabytes of disk space and eventually crash this container. Now, granted, your disks are probably much bigger out in the real world, but again, this is just an example. We took the default settings on length and width. Could be worse. Okay. So we're going to kill this. Okay, so that's kind of all I had right now. Please feel free to go to the GitHub link and download the code, check it out. Feel free to contribute to it. It's really easy to add a module. Also, if you have questions, I don't know if I have much time for them now, but I will be at 2 different Arsenal sessions, today at 3:45 and tomorrow at 1:40. Please stop by. I'd love to run through a lot more of the particulars of this tool. Also, feel free to join us. We have a Slack channel set up for this, ACSploit.slack.com. And again, you can email me or hit up our website. And with that, I thank you for your time, and we'll take any questions if we have time. Have you explored this against So yes, technically you could do this against mobile phone applications. In fact, we looked at some of them. We actually have hopefully we'll have a talk at another conference where we're going to talk about a couple of zero-day vulnerabilities we found, some algorithmic complexity zero-day vulnerabilities. Not specifically in mobile phone apps, but there might be some libraries that you might be able to use in a mobile phone app that might have these types of vulnerabilities. Yeah, so they definitely work, right? Any code could have an algorithmic complexity vulnerability, right? If you can upload an image, right, into a mobile phone app, then it might be vulnerable to an image bomb, for example. Anybody else?
How does it help you with your original problem of finding the issues?
Yeah, so for us, right, we were wondering if that blog post software, that message thread software, if it was vulnerable to a line break attack. You saw in just a couple of minutes, I can throw a bunch of test cases at it, say yes or no. If not, I can go on to the next algorithm I think it might be vulnerable to. So there's another version of that binary that all those words are stored in a hash tables for easy lookup for searching. And it's not vulnerable to the line breaking, but it is vulnerable to a hash collision. So think about all the things that behind that little text box. You could test all of them very quickly with ACSploit. Just generate the inputs, copy, paste them in, or upload them from a file. That's how it helps us with our original problem of triage. We don't need to spend hours looking through that code. We can spend a few minutes throwing a bunch of test cases at it and seeing if they land. Okay? Cool. If there's nothing else, thank you very much. Appreciate it.